Welcome to the section 8.2 notes. Today we're going to be talking about the trig form of complex numbers. We're going to be able to graph them in the complex plane, and we're going to be able to graph them in trig form, or also known as polar form. So the standard form, the book is always going to pretty much say z equals, is a plus bi. The trig form is going to be z is equal to r times the quantity of cosine theta plus I sine theta. So this a plus bi stuff is the stuff that we talked about a little bit as we were looking at the problems in 8.1. This trig form is going to be a little bit different. So the r is the absolute value or the distance or the modulus. So this is literally just like a radius. Okay, we are going to be in a plane. We're going to end up with a right triangle. Here's your r, here's your theta. It's no different than what we've talked about pretty much all semester. The argument is what that angle theta is, but it's important to note that it is the smallest positive angle to the positive x-axis. These things down here are going to be helpful, so that r is equal to the square root of a squared plus b squared. That's your distance formula. That's your Pythagorean theorem. Okay, your a is your x distance, your b is your y distance, r is Pythagorean theorem, square root of a squared plus b squared. And then these cosine of theta is equal to x over r, sine of theta is y over r, tangent of theta is y over x. That's stuff from earlier this year. All right. So when we are graphing a number in the complex plane, graphing is always going to be a vector. Okay, the tail is going to start at the origin, and then we're going to end at some point like 3, 4. So 3 to the right, 4 up. We're going to end at this point. There is your graph. All right, you have to draw the vector. I'll zoom in here a little bit. You have to draw the vector. It's just going to the point where the real part is your x value, essentially, and then the coefficient of the I, that's going in your y direction, essentially. That's all that's really happening. So this is our imaginary root, or imaginary axis, and this is our real axis. All right, so next up, we are going to find the modulus and the argument for the complex number and write this complex number in trig form for a complex number. So it says round to the nearest tenth where necessary. This is the thing we just graphed. So I'm going to draw a quick picture off to the side here where we had, this was our r, this was 3, this was 4. Okay, and then theta was in there. It was a right triangle. It was a terrible right angle. Let's try that again. It was a right triangle. So to figure out r, this is the square root of 3 squared plus 4 squared. Okay, that's from the formula that we showed 2 slides ago, and it's from the Pythagorean theorem in this triangle. So r is equal to the square root of 9 plus 16. So r is equal to 5. I'll make that a little bit nicer. I said a little bit nicer, and then it was about the same quality. All right, so since r is 5, this is also known as our modulus. I'll put a double box around that. Okay, the modulus, the radius is 5. If I want to find the argument, so to find the argument, well, I can go based off of this triangle. I could do sine of theta is equal to 4 over r, which is 5. All right, well, then theta would be sine inverse of 4/5. Or I could have done cosine of theta is 3/5. So theta equals cosine inverse of 3/5. Either way, when I plug these in, I should get that theta is approximately 53.1 degrees, since it said round to the nearest tenth. All right. Now, for some of these, like this is not one of the basic things from the unit circle. There will be problems where you're using numbers from the unit circle where you have 2 possible answers, because remember, it's the smallest positive angle. Since I had already drawn this, I knew that we were in quadrant 1. I didn't really have to worry about it. But I should pay attention to this thing had 2 possible answers, this thing had 2 possible answers. Make sure you find the one that works for both of them. So number 2, we are going to write this thing in standard form. All right, so this is in our complex, our trig form. So z is equal to r times cosine theta plus I sine theta. And that's the same thing as z is equal to a plus bi. All right. Variables are kind of unnecessary at this point. You could use x's, you could use a's, whatever. So I'm going to do this kind of two ways in a sense. I'll talk through them at least. So my first thought when I'm looking at this, if I'm not really sure what I'm doing, I'm just going to kind of draw a rough idea. So this is my radius, so that's how long my vector is. I know where 120 degrees is, so 120 degrees is over here, right? So that means I had a reference angle of 60 degrees, and then that whole length was 6. Okay, I can think of that triangle where I have 6, right triangle, theta. I'll call it theta hat since it's not our actual angle. All right, I can think of that triangle and then try to solve for those things where theta hat is equal to 60, like we already figured out. All right, so in that case, I basically am just thinking, well, cosine of 120, that's the same thing as negative cosine of 60 degrees, which is square root of 3 over 2. All right. Sine of 120 is the same thing as sine of 60, which is 1/2. I did these backwards. Sorry about that. I had those ones backwards. So it's still negative cosine of 60, but cosine of 60 was 1/2, so this is negative 1/2. And this is square root of 3 over 2. I looked at my notes backwards. All right. Well, if I replace those values, I have 6 times negative 1/2 plus I times square root of 3 over 2. This becomes negative 3 plus 3 square root of 3 I. Okay. I abandoned this triangle and I just said, oh, I know what these values are. I replaced them with what they equaled, and then I distributed. That's all that happened. Okay. If you wanted to, you could, like I said, figure out this triangle, which is basically what we did here. Okay. If you did cosine of 60 equals something over 6, that's where you're going to have to come out and figure out that that would be a 3. But since we went left, it's a negative 3. And then this would be a 3 square root of 3. Okay. It's your 30, 60, 90 special right triangle would also be how you can solve that. So our standard form of 6 times cosine of 120 plus I sine of 120 is the same thing as negative 3 plus 3 square root of 3I. For number 3, we are going to sketch this one. So like I just kind of explained in the last one, you can do this based off of having this angle and knowing this radius. But I want to get it so that we have the actual standard form, because standard form is going to be a little bit easier to graph. All right, because then you don't have to worry about lengths so much. So I'm going to change this thing to our standard form again. Well, 210 degrees is equal to 180 plus 30, right? So I can think of my reference angle being 30 degrees. So cosine of 210 is equal to cosine of 30. Well, I think about my negative signs. So cosine of 210, that's going to be to the left. That's a negative. So there's that, which is going to be negative square root of 3 over 2. Sine of 210 is going to be negative sine of 30, which is going to be negative 1/2. So now I have 4 times negative square root of 3 over 2 minus I over 2. Which is negative 2 square root of 3 minus 2I. All right, so if I wanted to sketch this graph based off of this, I would be able to say negative 2 square root of 3. I'll just mark it right here, say that's negative 2 square root of 3, and then I'll say that's minus 2. Maybe put an I there. There's my sketch. Weird crooked vector, should have been straight. But I could also have hopefully been able to identify that, well, that's 210 degrees. Okay, this thing has a length of 4. Okay, there's 2 different ways to kind of go about these graphs. It's important that we end up with a vector, put a dot where it ends just to make sure you know that that's where it stopped. and you're good to go. So for this one, we want to write this in trig or polar form. So remember, we have z is equal to a plus bi, or you could do x plus yi. And that's also equal to r times cosine of theta plus I sine theta. So in this case, we need to figure out what r and theta are. Well, r is equal to square root of a squared plus b squared. Well, a is equal to 1, and b is equal to negative square root of 3, because this was a minus square root of 3. So r is equal to the square root of 1 squared plus negative square root of 3 squared, which is just going to be 1 plus 3. Square root of 4 is going to be 2. So we figured out what r is. Now I need to figure out what theta is. So this is where I'm going to talk about doing both pieces. So cosine of theta should be the same thing as the real part over r, so that should be 1 over 2. And sine of theta should be the imaginary part, the complex part, negative square root of 3, over the radius, which is 2. So we had to find the radius first, no matter what. So to figure this out, cosine inverse of 1/2 would tell us that in order for this to be true, theta would have to either be 60 degrees or 300 degrees. Those are the two times where cosine of theta is going to equal 1/2. For this one over here, sine inverse of square root of 3 over 2, negative square root of 3 over 2, I should say. Sine is negative in quadrants 3 and quadrants 4, so that's going to be at 240 degrees or 300 degrees. It's tempting to want to put 60 because cosine inverse of 1/2 equals 60 jumps out at you right away, but the actual angle is 300. So my final answer for 1 minus square root of 3i in trig form is going to be my radius of 2 times the quantity of cosine of 300 plus I sine of 300. All right. And then we don't need to simplify this at all, because if we simplified it, it would just come back to this thing over here. So now we want to graph this next one in the complex plane. All right, so again, I'm going to just kind of simplify this and get it back to our standard form. So I can think of 240 degrees as 180 plus 60. So our reference angle is 60 degrees. So I have 2 times the quantity. Well, cosine of 240 is going to be, let me change to red for this. We have cosine of 60, but cosine of 60 is on this side, cosine of 240 is on this side, so it should be negative cosine of 60. And then we have plus I times sine of 240, which is going to be sine of 60. But if I think of that, sine is positive up here, 240 is down here. I'm actually going to have that be a negative, so I'll just change this from a plus to a minus. You could have I times negative sine 60. It's basically the same thing. All right, so now I have 2 times, well, cosine of 60 degrees is going to be 1/2. So I have negative 1/2 minus sine of 60 degrees is going to be square root of 3 over 2. So I have I square root of 3 over 2. Now if I multiply that stuff by 2, because I'm distributing, I'm going to get negative 1 minus, I'll put square root of 3 in front of the I. So I get negative 1 minus square root of 3 times I. So the real part on the x-axis, here's my negative 1. The imaginary part on the y-axis, I'll put as negative square root of 3. I go to that spot right there. There's my vector in the complex plane. Because here's my real part, here's my imaginary part. It would have our x always be real and the y always be the imaginary part. So there's your assignment. Again, make sure if you're having questions that you ask them. We are almost done with this quarter, almost done with this semester, so these last couple tests are going to make a big impact on our grades. So don't hesitate to reach out with a question, and I hope everybody has a great day.